Alright, this problem here you can interpret as a mass spring Dashpot system. The mass is 1, the damping constant is 2, the spring constant is 1. It's got the initial position and the initial velocity. So maybe the initial position is 2 feet to the right of the equilibrium. With velocity 2 feet per second to the right, okay, because they're both positive. Okay. And then the right hand side here is the external forces. There's two of them. The delta t, that's like hitting it with a hammer at time t equals 0. And then the delta t minus 2, that would be like hitting it with a hammer in the opposite direction at 2 seconds. It's the opposite direction because there's a minus sign in here. Okay, so we're going to see what this mass does. So we're going to take Laplace transforms. The Laplace transform of x double prime is going to be s squared x minus 2s minus 2. Then we're going to have plus 2 times Laplace transform of x prime, which would be sx minus 2. Then plus Laplace transform of x, which is capital X. That's equal to e to the minus 0s minus e to the minus 2s. Those are the Laplace transforms of the delta functions. Okay, so you've got s squared x minus 2s minus 2 plus 2sx minus 4 plus x equals 1 minus e to the minus 2s. Alright, so if we collect everything that has an x in it, we got that. We also have a minus 2s, and then minus 2 minus 4 is minus 6. That's 1 minus e to the minus 2s. In the parentheses here, you'll notice that that is s plus 1 squared. And then if I move the other terms over, 6 plus 1 would be 7. We'd have plus 2s, and then still minus e to the minus 2s. Okay. And then if I divided both sides by s plus 1 squared, I'd have x is 7 over s plus 1 squared plus 2 times s over s plus 1 squared minus e to the minus 2s times 1 over s plus 1 squared. And I'm even going to rewrite the first term. I'm going to put the 7 out front, just like I did with the other ones. Okay. Now I'm going to label things here. So this first one I'm going to call capital F of s. Okay, capital F of s is going to be 1 over s plus 1 squared. Notice that this would be the same thing. And you can look up in the table, that means little f of t, right, the inverse Laplace transform of that guy, would actually be, it would be t e to the minus t. Okay. Now, the guy in the middle here, let me call that g of s because it's different. And there's a couple different ways to break down g of s. Now that function is not in the table. You're not going to find it. But you could do partial fractions to rewrite it. Another way to do it would be to realize that g of s is actually just s times f of s. Okay, and if I wanted to, I could also say minus f of 0. Why am I allowed to do that? Well, because f of 0 is just 0, so I'm allowed to subtract 0. That doesn't really change anything. The advantage to that is that this actually looks like something in the table. That looks like the Laplace transform of f prime of t, which, what's f prime of t? You could just use the product rule. it's t, it would be, you know, it'd be e to the minus t minus t e to the minus t. And so that must be little g of t, right? Because it turns out that's the thing you got to take the Laplace transform of in order to get that capital G of s. Okay, so a little trick there. If you wanted to just do partial fractions to do that, you could have done that also. Little x of t, what is it? It's going to be 7 f of t plus 2 g of t minus, and then here's where we see that exponential, so it would be u of t minus 2 times f of t minus 2. Okay, and I think I'm just going to leave my answer like that. And, you know, of course, you could take it further by actually plugging in the formula for little f and the formula for little g and writing it as a piecewise function, but I'm just going to leave it like that.